So today is the last stage, number 5 of CNT Internships and training. Okay. We want to show you the types of results of 3D technology that can be reported to the client. Um, so let's check what we already know. We know that they use hydro separator, the electric pulse disaggregation, etc, etc. And the main thing that we not just commute the sample and beneficate it or enrich or make hand picking, but also we use the whole amount of data, the information for our special analysis, for petrography, mineralogy and chemistry analysis. You know very good this flow chart already, and yeah, let's hear. So while we are using the EPD Spark 2 and hydro separation SHES 11, we already see and know of which minerals the source sample consists of. So if we list them, we can make a special task for electron microscopy operational personnel to do the microphoto and electron probe microanalysis, as we need it exact for the client. Alright, okay. So there are a lot of data, but we use kind of standard for representation for the client. For example, we can check the grain size distribution of specific sample, and it can be demonstrated by diagram. Also, I will show the exact report a little bit later. Just let's take a brief look on what we do, on what we can design to show for the client. Also, we can check the chemical composition, and also it can be demonstrated both in histograms and tables. So what's the difference? The tables are more likely because you can very quickly understand the main thing. For example, on this histogram is shown that from 5 samples we see 2 different samples which consist mostly of oxidized copper, and the otherwise the other samples consist of sulfide copper. This is very important for mineral processing on plants, for technology, flotation or gravitation, enrichment, and etc. Also, we make tables. The main thing in any kind of tables, we do a lot of them. The main thing is that all the data should be easy readable, easy to look, and easy to understand. So for example, there are 1 sample and 8 uh, size fractions, and it is not so easy to fit a lot of data in one table, to put it on one page, So we use a special color identification of main cases. For example, we describe the minus 125 plus 71 microns size fraction as the main for the gold producing, as it has the best content of gold, and also there are a lot of and second gold rich fraction is 71 to 45 microns. These two fractions are very rich for gold, but also they are rich for sulfur, for arsenicum, for iron and stibnium. So this would be a case for technologists to make a proper separation of that. And also we highlighted that the finest fraction, 45 to 10 microns, contain a lot of palladium here. So palladium is mainly concentrated in the finest fraction. This is a main goal. This was a main goal of that report. What I'm showing you is the previous work, previous studies, previous research on different objects, and the main thing that I want to show you is that any kind of data we obtain, we can analyze and how to say that, pack, make a special packing for every client, exactly what he wants to see. The next thing that we can also analyze waste is tailings of hydroseparation. For example, in the tails of hydroseparation for the finest fraction, there was a very big content of palladium in the finest fraction. So we use a color, we use a special font, and also we use a special size of that font. After that, after we check the chemical composition of each fraction and sample, we can build a special correlation matrix, correlation table, which highlights as which elements have a very tiny connection with each other. So for example, this exact in this exact case, we see that the highest correlation coefficients are for aurum, gold, sorry, sulfur and arsenicum. Which means that gold, from mineralogy, we can make a decision that gold mostly connected with arsenopyrite. And also we proved that by our electron probe microanalysis and microphotos. And as we know, with which minerals we deal, and we know chemical composition of each mineral, we can analyze the mineral balances of minerals and heavy minerals for each sample or probe. A little bit later I will show you how we do that. So also we can analyze the balances of mineral during electron microprobe analysis and during making electron microphoto using characteristic X-ray reactions of mineral phases with electron beam. Also we can analyze real chemical composition for each mineral and analyze how much they content forgot a little bit. Just a moment. Oh, how much we can analyze how much mineral various mineral can contain mineral resources. I mean, for example, there are 12 mineral species of copper, sorry, and we know in each mineral species how much copper they are content. And we build a special crystal chemistry for formula. Sorry. All right. Yeah, formula. Average crystal chemical formula or stoichemic stoichemic stoi 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 stoichiometric
Average crystal chemical formula stoichiometric.
stoichiometric. All right. Stoichiometric formula. And also we make a special statistic table in which we show how many grains we studied, how many of them were fully liberated or stay in intergrowths. For example, we observed there about 468 grains of pyrite and 64 grains of intergrowth of tenantite and pyrite, 59 grains of halca-pyrite with pyrite, 34 intergrowths with magnetite, and etc. etc. To summarize, we studied in this case 238 intergrowth grains and once again 468 fully liberated grains. All right. And also we can measure the real size, the real grain size distribution, because we use a special parameter named equivalent circle diameter. This is a diameter of circle which equivalent in square of electron image of every grain. So a little bit later I will show what I'm talking about. And okay, for example, so we can see there several types of gold grain. I mean, some of them are fully liberated, they consist only of gold, native gold, and some of them are stayed in intergrowths. For example, there are intergrowth of pyrite, inclusion of pyrite in native gold. There are simply intergrowth of native gold with pyrite, with galenite, with tetrahedrite, with halca-pyrite, and etc. etc. So we can measure the square of each grain, and more of that we can measure square of only gold and only of pyrite, and make a special statistic on that. When we're talking about more than 400 grains, this is a very good statistic for analyzing, and so we can say that our data is very representative. All right. For example, let me show a simple flow chart how we do that. We do that using a special program ImageJ, and now we are working on automated special software called 3D technology software, which will allow us to automatically analyze all the needed data for our investigations or task of particular study. All right. So here we can see the electron image of grain and analyzed two dots, I mean two spectrums. So there are two phases, two mineral species only. We can decode this, for example, with red color, and red color is represents the square of pirate here, particularly there are pirate, all right, and white one is a halcoxide. So we can analyze the pirate square and halcoxide square, and count an equivalent circle diameter for each of them. So for example, there would the equivalent circle diameter of pirate would be 530, and equivalent, or sorry, let me say ECD. ECD is the abbreviation of equivalent circle diameter. So ECD of halcoxide is almost 300, and if we analyze them together, we can say that almost 70% of grain is consisted of pyrite and only 30% consisted of halcoxide. This is a very important information for any technologist who has to beneficate such type of ore. So if there would be any problems with obtaining the final concentrate, flotation concentrate, we can say that technologists should take his view more on pyrite, to use special depress, for example, to use special depressors to reject the pyrite during flotation process, or otherwise he can directly work with the halcoxide. Sometimes I should say that sometimes people do not know what they are working with. I mean, sometimes people doesn't know the real mineral species in their ore, and it goes to the biggest problems in the mineral process in the big volumes. I hope you understood what I mean. Okay, so the next thing, I would like to show you the products we received on sample we showed you past days. This time we packed them in a special. Oh, let me just make a little bit like this. All right. Okay. Okay, I'm still there. Just a moment. Okay. Okay. So we packed them in a special thin paper convert envelope. Oh yeah, envelope. Yeah, yeah, envelopes. But mostly we make a special tablets, polish thin sections. It looks like this one, and we really have a lot of them. So I think you really now know why we use these monolayer polish thin sections, because we are cutting the grain right in the middle of grain. We use narrow size fractions, and just a moment, use a narrow size fractions, and as we cut them right in the middle of their section. So we can say that this is a maximum sizes of each grain we observe, and sometimes we have from 2 to 5 times bigger sizes that are previously known in literature, in science publications of different objects. Just because we use EPD technology, as it says the source sizes of different minerals, and also we use a narrow size fractions and separate them with a hydro separator. So there are very good hmm, very good very good separated and sorted, yeah. But this time we just made hand picking, and we'll return that to the client as they want to analyze these grains with isotopy methods, with gaze gas isotope methods. You can see that the grains are really small, and this is actually a heavy concentrate, a Sches concentrate. We did not make hand picking from that because it is almost impossible. This is the finest fractions, and there are a lot of sulfides here. This is a minus 45 micron fraction. All right. So after we receive that kind of monolayer thin sections, we do we pulverize them with we coat them with a carbon, and after that we do an electron microscopy and electron probe microanalysis investigations. Let me show what kind of data we receive. So for example, oh sorry, just a moment, I'll move the camera once again in its place. Okay, so alright, so you can see that. So for example, this is gold stibnium deposit, and once again we see there a Sches concentrate. This is a very small amount of Sches concentrate, because the main goal was there to find gold grains, and we did that very well. So mostly we can see there arsenopyrite and stibnite. Okay, this is from reflected or reflected light or microscopy photos, and we can see the arsenopyrite with the pyrite inclusions in it. Okay. And this is actually once again, this is actually reflected light or microscopy images, and this is already electron backscattered electron or secondary electron microscope images. This is color decoding from characteristic X-ray reactions. So we can see that each grain analyzed for main phases. We can see there at least three phases, mineral phases. This is phase 1. It goes there, and there. Phase 2 goes there, and there. And phase 3 goes in a dark gray color here. Each analyze, each spectrum goes with a special uh, Excel table. Let me show you the tables. Okay, just a moment, it will load it. So okay, just a moment, still loading. So yeah, each each micro photo goes with a special Excel table, which describes the chemical composition in phases we analyze. So for example, this is a third sorry, I missed, sorry. Okay, next image. Yeah, so for example, this is a fourth image, and we see that spectrum 1 is consists mostly of stibnium and sulfur. So as I know, this is definitely stibnite. The same is for spectrum 2 and 3. So we know that spectrum 1, 2 and 3 is stibnite, but spectrum 4 is definitely pyrite. And also we can see by morphology of this intergrowth that it looks like cubic pyrite, and spectrum 5 is arsenopyrite. I think that this grain mostly consists of arsenopyrite, and the last one, spectrum 6, it's here, consists of stibnite. I think this is the whole arsenopyrite too, and this grayish, dark grayish, is cubic pyrite too. You see, morphology is very similar with a cubic pyrite. So this is a very simple example, but sometimes we can receive a lot of data. Let me show you real field data. Just a moment, I will find it. For example, one of the last work on phosphorites. Yeah, that's what I mean when we analyze more than 100 grains, more than 1,000 of such tables. And the trouble is that sometimes they are analyzed in element form, sometimes they are analyzed in oxidized form, and this is really hard. It's not so hard, but it takes time to make a special processing for analyzing before analyzing these data. So we develop a special scheme, a special table for counting the real mineral species. Also, I forgot that sometimes analyses are bad. The how we check bad analysis from electron microscopy or good, we can check the sum of content of various elements. So if you see 100% from electron probe microscope analysis, let me say abbreviation again, EPMA, okay, EPMA. So if you see 100% sum of EPMA, this is definitely not good analysis because it was normalized, and then operator normalizing the analysis, we lose the information about elements which cannot be detected using electron microscope. For example, this is um, all volatile elements as hydrogen, oxygen, uh, and light elements. Oh, sorry. Let me show you also. Okay, light elements like lithium, beryllium, bore, carbon, nitrogen, sometimes is phtor, helium, and etc. etc. The main element we have to understand how much of it in the sample is oxygen, and sometimes carbon, and sometimes hydrogen. But uh, it's not a big problem when analysis is normalized. We definitely can use our model for that. For example, here is example of what we receive from the electron microscopy operationist. After that, we transform that data from vertical to horizontal. So you can see each fraction is each analysis uh, placed in a separate column. Let me just make a little bit more width of each column, because it's impossible for you to see anything in this small scale. Just a moment. Alright. No. Okay. And once again. Okay, that's better. So you can see this is one electron microphoto, and there are 26 separate analysis. So all of them we placed in a horizontal view. After that, we used a special coefficient. We used masses of or weight of each element we see in this table. In this selection, I also can say. And after that, we do a simple arithmetic stage. So each we divide each content of element on its mass, atom mass. So for example, sulfur, we divide content of sulfur from pyrite to the atom mass of sulfur and receive a special coefficient. And we do that for each element, and as we use Excel, it is very simple to make a very big amount of data. We just pull up or pull down the whole formula. So we signed it one time, and then just automatically can reassign for each cell its um, value. Sorry. Also, as sometimes we doesn't know which mineral we see, but we can analyze of what cations it consisted of. Most of the mineral consist of I mean ore minerals or heavy minerals consist of one or two cations, and this is very important for future counting, future analyzing of minerals. So after we received the special coefficient, we also presumed how many cations it has. We have to count special coefficient. I mean it. We have to count atomic ratio of for each analysis. So to do that, we just summarize all the cations, the content, or sorry, the coefficient of each cations, and we divide the sum of cations for sum of coefficient for each element, and we receive an atomic ratio. After that, we do once again, we take our coefficient on every element and just magnify it, multiply it, multiply for atomic ratio. So you can see that for example, sorry, I just forgot that it maybe was unseen because of my camera. No. Alright, so as you can see, we receive in the end the indexes of elements, and now we can check how good we did our counting. So as we know, for pyrite, stoichiometric formula is ferrum sulfur 2, and we see the almost the same for our results. You see, ferrum is 1, that's because we counted for one cation, and actually in pyrite there are one cation made of ferrum or iron, okay, and a little bit more sulfur. That's why what I'm talking about when you analyze the normalized analysis. You always will receive some dis displacement in your results. I mean, some of the cations would be less or more, and the same for anions. Okay, all right. Also, I have to mention that there are two common anions which are excluded in counting of atomic ratio, is sulfur and oxygen, as they almost almost always almost always um, stay in the position of anions in crystal in a crystal cell. Okay, so and the same operation we repeat for every single analysis, and as I said before, there could be thousands of that analysis, and we think that this model is the best choice when you analyze a lot of um, data from one sample. Okay, and next thing that I would like to discuss is mineral balances counting. So as we know, the whole chemical composition of the source sample. I mean, uh, how many percent of elements are in the sample, how many content of particular elements we to detect them. We use several methods. It could be ICP mass spectrometry, atomic emission spectrometry. It could be fire assay. There are a lot of them, but all of them uh, give us information of content of elements in percent or ppm. So for mineral balance counting, we use only percent. So if you have data in ppm, in parts per million or grams per ton, you have to count that to percent, mass percent. To do that, you just put your sorry to do that you just you have to divide your content in ppm to 10,000. As you know that in 1% there are 10,000 of ppm. Okay, so as we know the whole composition of source sample and know the chemical composition of each mineral phases, mineral species we observed in the sample, sometimes we can use the literature data as web mineral or or Mindat web mineral. Oh, sorry, web mineral, webmineral.org, yeah, or .com, yeah, .com. So for example, pyrite mineral data, and in the upper part of our window, come on, yeah, we can see the content of particular elements in this mineral. That's we use the use then the data is not enough for building the average stoichiometric formula, or analysis are very bad. But as we use a lot of data, we are trying to use only our data. Sometimes from object to object, I mean from one deposit to another deposit. Minerals can vary in content of particular elements. Sometimes pyrite more sulfury, more irony. It depends on circumstances, and also from a genesis, particular genesis of deposit. So we know chemical composition of every mineral we observe, and we put them into a special tab, and after that we can analyze the content of mineral using our chemical composition of source sample. How to do that? This is not so simply to show, but we will try to make a special lesson, separate lesson on that. We have special lessons actually in Russian, but in English it's a little bit harder for me. But soon I think it will be done, in a few days or weeks. It depends how good we will meet a new year, you know. And for example, with the bold font, there highlighted the content in percent of each mineral phases we saw. Okay, so as we know that in a source sample only 5 or 0.005% of titanium, and we see there only one mineral of titanium is titanite or sphen in old publications and literature. We can count all the titanium to titanite using this simple proportion scheme. The same we can do with barite, as barite is the single mineral bearing the barium. Same we can do for chromium and chromite. Same we can do for galenite and plumbum. So we count them as the single bearing minerals for these elements. Why is it is important? As we counted the content of particular mineral by elements, we also can count how much another elements are connected with that minerals. I mean, we know that in this sample there are 0.005 percent of barium, and also we can count that 0.0006 and etc. sulfur in percents are connected only with barium. But sulfur in a source sample is about 1.7%. So most of that sulfur is connected with another sulfide minerals. Okay, and we repeat that for every mineral. Sometimes there are troubles to analyzing, to counting minerals, as we know that one element is buried, is hosted in for example three mineral species. For example, there are chalcocite, chalcopyrite and bornite. But using our investigations of source material, as we see all the data, all the microphotos, and measuring the squares, measuring the balances in intergroves, grain sizes, and etc., we can analyze the balances of these particular mineral species. For example, we studied there, sorry, yeah. So, for example, we studied there that from chalcocite and chalcopyrite and bornite, the distribution is R distribution is 85% of chalcocite and only 10% of chalcopyrite and only 5% of bornite. We counted that using information of square and equivalent circle diameters, using that exactly information. Sometimes when we are short in time, we can use the information of mineral balances from color coding, from characteristic X-ray reactions. Okay, so for example, we see the red, blue, I don't know how to name that color. So for example, at this particular photo, we can see 5 faces and measure them, their content in a histogram, and use that information in accounting of mineral balances. So I am oftenly asked, why is mineral balances so important? And my standard answer is that if you want to know with each object you are dealing with, or with each ore or type of ore you are dealing with, you have to analyze not only chemical composition, but you have to analyze real mineral distribution And the trouble and sorry as and this is important as the each mineral has its own physical and chemical properties. So for example, at this work, guys tried to flotate to receive copper concentrate for copper flotation concentrate, and they um, were were aimed for the main uh, copper host copper bearing mineral as chalcopyrite, but they showed them that the main copper bearing mineral is chalcocite, and they have a very different properties for flotation, as the chalcocite is the content of copper in chalcocite is more. It has another uh, properties for flotation, and etc etc. The express way of receiving that amount that data is to proceed or perform diffraction analysis, uh, XRD, but it has own limits, as the when the content of particular mineral less than 1%, it is impossible to say is that analysis true or false, because uh, when you analyze diffraction scheme is analyzed by real human. You know, I mean, the more operator is experienced, the better data you receive. But we are trying to get out of uh, dependence of experience of our colleagues, and we are trying to fully automate all that analyzing processes. And once again, the main advantage of such approach is that we can work with a content less than 1%. And also I have to mention that um, the percents we're talking about counted for the whole balances. So if you summarize the percents of these heavy minerals, there are only there are only 4% for that fraction. For that minerals, there are only 4% of the whole material. That means that other 96% are consisted of not ore minerals. They are consisted of light minerals like quartz, like plagioclase, like pyroxene. Some of the pyroxene are really heavy too, but we are using ore microscopy to detect the real minerals which bear real mineral resources, you know. So if the task was to analyze how many pyroxene in this sample, we definitely just perform or proceed XRD, but if the amount of pyroxene were small, for example, in accessory studies, in accessory cases, yeah, we counted. We would like to count pyroxene too. So the list of minerals analyzed for mineral balances is also depend on cases and tasks which client gives to us. In this particular case, there was enough to analyze the sulfides and some other heavy minerals like pyrite tatanite, and etc. etc. This is an example actually from copper porphyry deposit. Maybe some of you know that Mikheevskaya deposit. And there are another um, example from gold stibnium bearing deposit. There are sphalerite, zinkenite, halkostabite, ulmanite, stibnite, arsenopyrite, and pyrite. Just 7 minerals. Their stoichiometric formula, their content in elements, the whole amount or the whole composition of the sample, and also there are counted mass percents of each mineral. Alright? So there are only 11, almost 12% are consisted in heavy minerals, but another 88% are presented by quartz, by chloride, by schists, and etc. etc., which are not so interesting for beneficiation, because the main goal is to understand how to get stibnite concentrate and gold with arsenopyrite concentrate. Alright? And also I would like to show you the final you have to understand that these cases to count the mineral balances, to count the stoichiometric formulas is not common, but we try to understand the substance we investigate. We always try to investigate the substance we receive, the samples we receive, as much as we can. But in this particular case, with the probes you disaggregated and wet sieved and hydroseparated and hand-picked with us, this is just a simple approach to receive the special products, actually sulfides, and we made a special list or registry of each product we received. So as you remember, the sample was only one, and we received 31 product to be analyzed. That's why we are talking about 3D technology. From one sample we receive a lot of samples, and when we study them, we study the whole amount of that sample. Unlike common approach studying in just in thin sections, when you receive random sections, and to receive the same representativity you have to analyze more than 100 thin sections. So I can talking about advantages of this technology forever, but let me show you the final diagram of grain size distribution. And we can build the tables once again, tables for product Spark 2 and product for Spark 10, but tables are not so good for showing. That's why we are trying always to build the histograms, as we can show anomalies, the anomaly distribution much easily. And more of that, after we build the registry, we build the grain size distribution tables and histograms, we build a smart report about the work we've done. So, as I said, we have a special standard for reporting, uh, which regulates the sizes, the fonts, the position of each value in each cell, and etc. and etc. And we cannot just copy this data and paste it in our report, as it would be non-informative at all. We always have to design our report. And after report, we also show the source sample, the EPD Spark 2 and Spark 10 products, the wet sieving products, and HS or hydro separation products. And also we try to make a micro photo of each fraction we proceed to for hand picking. So as you can see, there are a lot of intergrowth of sulfides, and also there are a lot of monomineral grain of sulfides. So that's all. I think that's all I wanted to show you today. Let me check my plan. Alright. That's it. Okay. Okay, let me show you also how we analyze the grain sizes and the equivalent circle diameter, and also maybe I could show you how to design the grain photos. Oh no, I cannot do that because I have another workstation. I have a streaming workstation with not pre-installed img and Photoshop, but okay, let me show on example done. So I have to mention the one main thing that I tell every students, that the more labor you will do the report, the more easy client will understand that. What I mean, for example, we have that type of source image. As you can see, there are no any signs of mineral we observe, and also we have very little scale line here. Scale bar, sorry. Yeah, we have a very little scale bar here. So using different image reductors, I mean image editors, we can move this scale bar, and also make font bigger, because I cannot see how much scale here. Okay, it's impossible. That's why we move separately. We move scale bar on each photo, and also trying to sign each faces with a big letters, you know. Just take a look on each photo and you will understand what I'm talking about. Also, when we are talking about, let me show you mm, some of reports, and that will be easy to understand. Okay, okay. Public, public, where are you? Public. I can't find public catalog. Oh, okay, okay. So, all right. Let's take a look. All right, all right, all right. So here you can see a standard kind of standard report. There are 5 samples of um, source rock were investigated, and also additionally we investigated 2 types of concentrate, flotation concentrate, to understand which minerals are harmful for beneficiation, and how to optimize how to proceed the optimization of the technological uh, flow for receiving the conditional concentrate, and etc. So this is a standard scheme of our investigations. Photo of sample preparation. Alright, tables, histograms, a lot of histograms, chemical composition. You see, this is one of the best composition of a chemical table we've done ever. So there are 3 primary rocks, 3 oxidized or two oxidized rocks and 2 concentrates. This is the comparing. Oh, sorry. This is comparing of chemical composition of various of different types of samples. You see, we use color to highlight what we exactly we would like to show our client. Also the histogram from presentation, also correlation table or matrix, correlation matrix, and the most interesting chart of our report is the mineral composition of samples. So once again we observed 12 mineral species which are bearing copper. More that we observed that amount of another heavy minerals. I don't know exactly any kind of technology which allows to observe so rich mineralogy just from from 2 kilograms of sample. This is the results of X-ray diffraction analysis. That's what I'm talking about. When they see the content less than 1%, we can simply get out simply sorry reject okay, we can simply reject the content of such contents because they are not representative. But in when we are talking about big contents of another minerals, X-ray diffraction analysis works very good. for example, there are 41% of quartz and 22% of muscovite, and etc etc. Sorry, I have lags. Okay, this is a summarized table for mineral balances counting, and I would like to, yeah, I found that. Yeah, good. So what I'm talking about, each figure is consist of several, for example, there are 18 microphotos, and each microphoto should be processed in a particular way. We have to sign every single phase we observe in grain in intergrowth. So, for example, there are quartz, there are pyrite, there are rutile, and also there are epidote. Epidote, yeah. It is good to also to make us some kind of sorting when we deal with a lot of uh, similar photos. So for example, we are sorting by the size of grains. Sometimes we are sorting on mineral assemblages and associations. Sometimes we are sorting by the um, ba balances between intergrowth. So sometimes we are starting from pyrite and end with copper bearing minerals. All right. Mhm. Also, I have to mention that in a singing um, signature of each figure, we have to make decryption of abbreviation we use, so not everyone knows what is TENN. That's why we put a special decryption in the signature of our figure. TEN, this is a tenantite actually, and his known formula is shown also there. Also, it would be good to show on which equipment was received such photos. So for example, we received that by Leica DC300, and the same information is for every sample we studied. So first of all, we are talking about the um, tables. We are building tables describing mineral compositions and relationships of host rock minerals, ore minerals, and accessory minerals. After that, we put the images of that minerals and intergrowths and their relationships with each other. And here we separated the images from reflected light or microscopy and from electron microscopy. So there are a lot of beautiful grains. You see, this is not I really keen on to when I'm thinking about that these I ideal square or ideal cubic grain was made by nature, not by human, you know. And also inside this grain we found another mineral. So this cube is gertrophite, and in inner space is pyrite or phedsonite. This is actually a light mineral, and also mineral resource is bornite, is copper bearing mineral. And then when you are looking for all that information, when you have sorted it by your own, you have uh, uh, a special mm, imagination. I mean, mm, sorry. I mean that when you sort that information by your own on object or on one single sample or probe, you have you receive a clear picture. Clear picture appears in understanding not only genesis of this object of these minerals, but also you have understanding how to receive a special products of that. I mean, you can speak, you can mm, prove, you can make decisions to how to beneficate that, and more of that. You always have to prove and always have the data and information to show, to prove your words, so you always can say that I know that better because I've seen that. Okay. And in the end is the results of analyzing the process product, flotation concentrate. Actually, we found the 4 gold grains, but the client told us to cut off that information because in Russia there are troubles with exploration of deposits, because if you have gold in your deposits you have to defend or not defend, you have to prove how many of that gold you have in your deposits. So sometimes we see what that we see what we should not to see, if you know what I mean. And in the end we talking about what we observed, what we analyzed. We make the several conclusions and build the special recommendations what we have to do more to analyze better, to close the white spots in our reports. For example, sometimes there are needed to proceed another analyzing methods. Sometimes we need more samples to analyze, and also we can tell to client what they have to do to process better, to receive better concentrate and better tailings, better wastes. For example, let me show you a simple flow chart we built for extraction with tungsten from slags after metallurgic melting. So this is a wastes of melting ferrotungsten. As you can see, we built almost always histograms, figures, correlation tables. This is another report, and we also can show what client should do to receive several products with which are feasible, economically valued, and etc. etc. Maybe I can find this in English and you will understand what I'm talking about. Come on. Nope. Nope. Oh, it's here. Yeah. So this is, for example, what we received after we studied brown iron ore and manganese ore. This is Ackerman ore deposit. And they build that scheme only using only one sample of brown iron ore and one sample of manganese ore. Sorry. Yeah. So there are two main stages: uh, coarse beneficiation and beneficiation of the fine fractions, -1 millimeter. If you're interested, you always can contact us. I will send you these flow charts and etc. etc. So I think I'm done. If you have any questions, you can always ask me or Vlad or Alexander.